You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Hello, this is Richard Jacobs with the Future Tech and Future Tech Health podcast. My guest is Aaron Johnson. He's an assistant professor of mechanical engineering at Carnegie Mellon University. We'll be talking about robots, getting him out of the lab and having him do real world stuff like navigating rocky hills and cluttered houses and things like that. So, Aaron, thanks for coming.
Thanks for having me.
Yeah, so it sounds simple, but how difficult is it just on its face to get robots to work in complex environments like people's homes or restaurants or outside various terrain?
Yeah, it's very challenging because where robots have been very successful is in factories and warehouses where we typically engineer the environment to suit the needs of the robot. So we know that the conveyor belt is perfectly flat and where it is with good lighting. And once we get out into either natural terrain or human environments, there's clutter. We leave things on the floor. Things are moving around, and the robot may not be able to see everything that it needs to see, and may not know exactly how it's interacting with that environment. And so the uncertainty that comes from these sorts of unstructured environments makes it much more difficult. If we knew exactly how heavy the box was and exactly where it is for a warehouse sort of packing operation, then the robots are doing quite well. But moving over broken terrain, uneven terrain, cluttered environments where we can't see what we're stepping on, that's where robots have a lot more trouble.
So how much do you have to borrow from the driverless car industry? So I think they're focused big time on driverless cars, and a lot of the same principles would apply to robots out in the real world.
Absolutely, and I think one of the things you see with the driverless cars is the initial sort of excitement with driverless cars was that it was a more structured problem. We have roads, they're relatively flat, and we can have a map ahead of time, and there's traffic signals. And so the sort of initial progress was quite rapid on those problems because we could sort of make some assumptions. And as all of these different companies are trying to get their driverless cars to be reliable, they're discovering, well, pedestrians don't always cross at the crosswalk, and the flat asphalt may not be as flat as we think, and the painted lines are sometimes hard to see depending on the lighting condition. And so they're discovering that even though that is an engineered environment, they're driving on paved roads with controlled traffic. There's still a lot of uncertainty that comes in, and that sort of that last little bit to get over that uncertainty is the challenge. And certainly all the excitement with multiple companies pursuing this is really helping to push forward a lot of the same sensing technology, autonomy algorithms that we would use on a mobile robot that's either walking around or on wheels in smaller spaces.
When you learn how to modify an environment to make it easier for machine vision to work and a robot to work, is there a way to take those learnings and apply it to people? Let's say a robot has a hard time distinguishing something on the road because of the poor lighting. So maybe that leads you to reformulate the stripe material on the road, the incandescence of it or the color of it, so that it's easier for people to see in bad lighting conditions. Is there any learnings back and forth by doing what you do?
I think there certainly could be. I don't know of any of the examples so far where it's gone in that direction. I can say, in my experience taking robots outside, the places where they fail are often places where you could imagine a human having trouble as well. So, for instance, we had a legged robot that was working. We were working on stair climbing, and so we went around to find every different type of staircase we could find in the area. And where it struggled were ones where there were clear glass panels, where there's sort of visual ambiguity, as well as sort of open riser and more industrial staircases that are actually harder for humans, especially if it was low light. You might also have issues in those same areas.
Yeah, so what did you, well, again, so in that exact example, you tried a whole bunch of different staircases. You found out which ones would be hard for a robot. But, I don't know, would it be even useful, or is it just kind of ancillary to what you're doing? It doesn't matter that you can inform places that are putting in stairs, for instance, hey, best practices is you don't use this kind of thing. Not only because in the future we want robots to be able to navigate your space, but because for people as well, it causes them issues, going up and down stairs. There may be this looking ahead, preparing businesses and environments to be more robot ready, more robot friendly. Maybe there's an angle there too.
Yeah, I think definitely the challenge is that in general, humans are so much more capable on the perception and autonomy and presence that they have, that we're sort of not quite at a level where we're sort of pushing the same boundaries always. But I'll give you another example on stair climbing specifically. There's some great YouTube videos from a particular subway staircase in New York City that over time has settled so that a single step is about half an inch or a quarter inch taller than the other steps. And someone set up a video camera, and you can see almost every human going up these stairs trip on that same step, because they think they're all going to be the same height, and they're just walking along. They're not looking as carefully at that stair, and all sort of stumble on that same step. And so certainly, as we start to get robots that are more capable of climbing stairs in general and are doing it more often, we might be able to detect some of these issues, that do affect humans as well. The other thing I'll say in terms of sort of improving spaces for robots, this is something where things like the ADA, Americans with Disability Act, is really pushing buildings and other human environments to be more accessible to different sorts of mobility, and that's definitely helped on the robotics side. A lot of robotics research for human environments will assume ADA compliant buildings, which of course most of our houses are not, and lots of those buildings are not. But it gives us sort of a good standard with which we can compare to.
So what are, pun intended, but what are the stumbling blocks to robots being able to operate in complex environments? Is it processing speed? Can a robot not react to the environment fast enough, or is it just a lack of enough data for the robot to figure stuff out?
I really think that the biggest stumbling block is the challenge that comes from the physical contact with the world. So for legged robots, but also wheeled robots and manipulation systems that are going out and physically touching the world, they're walking on rough terrain, they're picking up objects in clutter where they may bump into other objects, and the dynamics of contact are very discontinuous, meaning if I have my hand just above the table, I have zero contact force. And as soon as I touch down on the table, I can have large contact forces. And this means that any amount of uncertainty that we have in the system can cause large disturbances. So if I think I'm going to be just above the table, but I actually bump into it, I can very quickly lose track of where I'm going. And as we sort of no longer are engineering the environment and don't know exactly how flat it is or the location of objects, the fact that this physical contact is inherently discontinuous in nature is what makes it so challenging. And so we can be relatively good at perception and understanding the scene, but if we can be off by relatively small amounts and still have trouble.
Well, so are there stages where there's like sensing, initial contact, and then a feedback loop? Was the contact successful, and in the way that, does it correlate with the sensing? Like, I'm going to put my foot down on something. My sensors tell me that it's hard, but when I put my foot on it, I slip, or it's a crumbly surface. Does that loop happen with robot vision and sensing?
Absolutely, and that's the way that we try and tackle this, is trying to sense the environment as well as we can. But then if we're not certain if we're touching something, then we have to sort of slow down and really try and feel the world. I would call this sort of proprioception, so some of your internal senses of force and position, to see if you're really contacting the world the way you think you are. But we also need to, in terms of what the limitations of current robots are, we need to have better control algorithms that aren't trying to perfectly map out the entire world and exactly when you're touching each part. We need to be designing robots that are capable of succeeding even if they do bump into the chair as it's walking around, or when you go to pick up your coffee mug, your hand brushes along the table. That's okay for a human arm. We kind of bump into things all the time, and our control systems are just robust enough to this contact that it's not a problem. If we coming from a direction of assuming we know exactly where all the objects are and all the forces that we'll experience, leads to this sort of brittle behaviors that limit their capability.
So, what do you do? What makes the behavior brittle? How can you make it more robust, like a person?
So in my lab, we study the properties of the dynamics in and around contact events and thinking about uncertainty in order to design controllers that are inherently robust, that can work kind of no matter when you touch down or no matter what contacts you're making. And this sort of, by analyzing the structure of these dynamics, we can start to overcome those. I think the other important thing to look at is just trying to sort of push the boundary of what the robot can do. And maybe a lot of the stuff we do in the lab, maybe the robot can't do it reliably enough to be deployed yet, but in a sort of research setting, looking at what types of terrain could we get over and with different morphologies, different control strategies, and that's what's sort of exposing these limitations around contact and uncertainty that drives our research.
Well, what are some of the specific things that robots are worst at? What are they just bungle completely, and what are they good at?
Yeah, I think I would say when you watch these great compilation videos of robots falling over and failing in different fun ways online, and the common theme that I see when I look at that is that either the robot tried to grab onto something and didn't, meaning that they missed the contact that they thought they would have, or their elbow knocked something over, or they made they bumped into the environment somewhere else and ended up pushing against a wall that they didn't know about, and that led to the failure sort of down the line. But it all sort of started with the robot's assumption about its contact conditions was different than what was actually happening.
Well, is there a trade-off between the robot seeing in complete 360, both vertically and horizontally, and too much information coming into its processing system? Like, I'm picturing robots right now, and we want to anthropomorphize them. Like we look ahead and a little bit to, a 45-degree field of vision, but a robot, I would think, to be effective, needs to be aware of all its surroundings at all times. So why would it bump into stuff? How come it's not seeing everything always?
Yeah, so I think there's really two questions in that. Sort of on the first one, in terms of should we just put more sensors on, and is there any sort of limit to how much information we can collect? And certainly, we do run into computational limits. We're trying to use as much sensor data as we can, as fast as we can process them. Computational limits are in some ways easier to overcome to a certain extent as computers get faster and parallel architectures allow us to process multiple sensor streams at once and build up a sort of more complete picture. One of the challenges, even if we could look out in all directions, if we're walking up a rocky terrain, we can't see on the far side of that rock. Or if we're picking up an object on a table, we can't see behind the coffee mug to see if there's another object that we would bump. And so there's some limitations that just come from visual occlusions to how much you can see once you're in these more cluttered environments. The second part of your question, I think, was asking more about, as humans, we have only two eyes, and they're in our head, and they're only looking sort of in one direction at a time. And so we know that it should be possible to work relatively reliably with much less sensing than a lot of robots have right now. A lot of robots have 360-degree, not just color information, but also depth. So they're getting a real 3D map in all directions at all times. And many robots have multiple of these kinds of sensors, which is much more than humans or other animals are using. And to some extent, I think that's a good indication that maybe we don't need as much perception as we have. But it's important to remember that we're working with different types of sensors. Our sensors are good at seeing different types of things, and we're also working with different types of actuators, different types of materials, and so we can sort of draw some inspiration from biology, but we don't want to be constrained to say, well, the humans only have two eyes. Let's only put two cameras on the robot, and they have to point forward. And we don't want to be sort of constrained by that.
Well, people have to have a reticular activating system just with their two eyes because they've taken so much information, and a lot of it needs to get discarded in order to operate efficiently. So I sense that there's this huge trade-off there. Maybe having 360 perception and, seeing things in infrared and visual and, et cetera, and seeing depth and all that, maybe we'll run into a wall of processing speed, and that we're going to have to give up those things. And maybe that's why nature has done it with every creature instead of creatures that can see everything in 360,
Yeah, so one of the things that computers are really good at is moving lots of data around and processing large matrices very quickly. And so I think that's something that on the engineering side we're much better at. What we're much worse at is things like intuition and a lot of the low-level sort of motor learning skills that sort of hand-eye coordination type skills that don't take a lot of processing in animals and humans, but that are very hard for robots to achieve. And so I think on using sort of camera and other exteroceptive visual perception, that's actually something that we're getting very good at in terms of the computational architecture and algorithms that we have available for that. And in some ways, it can be better than visual acuity, in that it can be 360 all of the time. But just because because of the differences in what biological systems are good at versus engineered systems, we shouldn't sort of throw away what we are doing well at on the engineering side.
So if you were to imagine, I was thinking like in the movie Terminator, and how in the movie, I don't know if it happened, but people would sneak up on a robot and club it in the head, But with what we're talking about, that could never happen because the robot sees in 360 all the time. So what would you imagine a realistic, futuristic, amazingly effective super robot to be like? Like, can you paint a picture of what that would look like, and how would it sense, and how would it move? And if you could have all your ideals right now, what would that be?
I think it depends on sort of what the task is. And one of the jokes that people say in robotics is, once a system actually works, we don't call it a robot anymore. So, for instance, if you wanted to have a robot that washes your dishes, well, we actually have a dishwashing robot, in your house right now. And so I think it's hard to sort of answer the question in general because it's very sort of task dependent. I will say if you look at the movies, things like Terminator or iRobot or any of these, they're actually all of these robots are shown as being very, in some ways, graceful. They're walking over whatever environment. They're not bumping into things, and these are the things that are much harder for robots to do right now. In contrast, we're actually better than maybe what some of these science fiction imagination of robotics is, in that we can have much more sensor data and we can do sort of numerical processing very quickly. So, for instance, if you imagined a robot to do, let's say a demanding human job, like let's say, accountant or something, then the accounting part, the thinking part of our jobs is much easier for the engineered systems to do. But the getting out of bed and putting clothes on and handling different materials and working in cluttered environments, we're much farther away from having robots that can do that part of things.
Okay, so what's the goal for your lab in the next, or your research in the next 3 to 5 years? What do you hope to accomplish specifically?
So our long-term goal is to build robots that can go anywhere in the world, to work on rocky, hilly terrain as well as cluttered human environments. And in the next few years, we're really focused on designing controllers that are robust to the uncertainty that comes from very rough terrain. So mostly thinking about outdoor terrain and building robots that can get over the kinds of rocks and underbrush and other obstacles that come along with that. And so we're trying to build these robots for several applications, and one of them that I'm most excited about in the next 2 to 3 years is environmental monitoring. So sending robots out into remote locations to collect samples to look for either contaminants or to monitor changes in the environment, and just sort of go out and collect information in locations that's very hard for us to collect sensor information right now.
Okay, just because of the harshness of the environment, that it would kill people or disable them? Is that why?
No, just that it's very slow and tedious to sort of go out into a desert far away from other infrastructure. And right now, if we want to collect data there, we send someone and we can generally actually get there, but it's very slow and expensive. And if we can build robots that can get over these kinds of challenging environments, we can be much more efficient in terms of processing the sensor data on board and deciding where to collect information in the future. But we can also just collect much more information because we can have multiple robots go out and continually collect data. And so we think we're working to use these robots to try and find contaminants that have entered the environment, as well as look at longer-term changes like desertification or climate change.
So is there a specific robot that you're working on, a specific application robot, or is it more broad what you're doing?
We have a lot of robots in my lab. Sort of different projects are working on different systems. Most of the robots in my lab are legged robots. And again, this is some of the bioinspiration coming in. Lots of animals have legs. They seem to be pretty useful at getting over this kind of rough terrain. But we also have some wheeled robots that have complicated suspension systems that make them pretty good at getting over this kind of rough terrain as well. And one of the longer-term research questions in my lab is trying to understand when do you need legs versus using wheels to get over different types of environments.
Anything you've learned about robots and motion and sensing that just really, I don't know, is just very surprising to you or very strange to you, or things that really pique your curiosity?
I think that what always surprises me is anytime we're working with biologists or looking at sort of animal examples, just how far behind engineering is from biology, where the little mice that are running around in your backyard are jumping over obstacles or squeezing through a tunnel or under a root and just moving around at a level that's well beyond what we can do now. And so we've been working for the last few years on tails as one example, and looking at how cheetahs use their tails or how lizards use their tails, and they're doing all of these different behaviors with them. It's all very fluid and natural. They didn't spend hours designing this trajectory to exactly achieve this one behavior. They just run out and jump over that obstacle and keep going. And so anytime we look at these kinds of examples, and then we go back to our robots that still trip and slide around and move relatively slowly, That's what I think is always the most surprising.
Okay. And what do you think is going to be possible for the industry in the near term, maybe 3 to 5 years, and then, longer term, 10, 20 years?
I think that the near term, we're really seeing a lot of progress in what we might call somewhat structured environments. And so there's lots of, obviously, self-driving cars, but also sidewalk delivery robots and warehouse robots that are now starting to work around humans and in areas where objects might be moving around more than they had before. And sort of the long-term trend is sort of how structured does the environment have to be? I mean, the robots that are welding your car frame together are in a box where the human stays outside the box, the robot stays inside the box, and they're just totally separated. And now we're starting to see this transition into robots being closer to humans in less structured environments, and I think that trend will just sort of continue, over the next few decades. What about
one quick thought? What about a distributed system? So if a robot's going to do a task, why does it have to be one robot? For us as a human, we're one person, so we have everything on board, all our processing, all our faculties, all our hands, arms, digestion. But for a robot, why couldn't you have, instead of just a single object, it has a component that flies, that communicates the body that walks, and then there's another component that does the sensing and that communicates to the rest of the robot. So you don't just have one thing, you have multiple small little robots that act in concert, but they're all really for the same task. So it's like a distributed system.
Absolutely. The trade-off here is how much redundancy you have to have. So now each separate robot needs to have its own mobility system, its own communication system, its own energy storage. So you have some redundancy that you have to pay. But on the flip side, you can now have specialization. And I think especially thinking about networked systems of multiple robots, there's no reason that they all have to work entirely on their own and independently. And in my lab, we do a lot of analysis on sort of scaling questions. Would you rather have one big robot or many small robots? And different physical properties scale in different ways. And so the classic example is the ant that can pick up, 3 or 4 times its own body weight because of the way the strength of materials and forces scale to smaller scales. So we have some smaller robots in our lab that individually can't lift as much as the big robot, but they're maybe 1/4 or an eighth of the weight of the bigger robot, but they can actually lift more than half as much as the big robot. And so thinking about some tasks are better suited to relatively small robots with multiple systems, while other tasks, if you have one big heavy sensor, you want to put that on one robot, and rather than have 4 robots trying to carry it together. And so we're definitely thinking about this trade-off, and in particular how the mechanics of materials and forces at different scales plays into this question.
Yeah, it's so interesting how there's always trade-offs, It's never a straight shot, and you got to find this balance, and nature seems to have, biology, like you said, has out-engineered us big time, and they seem to have, I guess by necessity, found this balance over billions of years. Well, very good. Any final thoughts on the process of robotics, or, if not, what's a good way for people to get in touch and find out more?
Yeah. So if people want to get more information, they can go to my website, which is robomechanics.net. And we've got lots of videos up with these different robots, and looking at, we also have a link there to one of the mini robots that I mentioned that we have as open source design. And so people can actually download and build one for about $200 to get a small legged robot to play around with if they want.
Oh, very cool. Okay. Well, I appreciate you coming on the podcast. Thanks for the info. It's going to be interesting to see what comes in the next few years.
Great. Thanks for having me.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you.